Good afternoon, ladies and gentlemen. My name is Valdemar. I work at the Federal University of Goiás in Goiânia, Brazil, and I'm going to present the paper entitled Model-Based Engineering and Simulation of Software-Intensive Systems of Systems, an Experience Report and Lessons Learned. This paper reports actually our experience in a project developing system of systems in the last 5 years. We are working on system of systems. It's the idea that we have multiple constituent systems, independent and interoperable systems that are put together to offer more complex functionalities that they couldn't offer when working alone. And these systems have received software in their structure, so we have considered them software-intensive system of systems. And an instance of this is the smart cities, for example, when you have autonomous cars, you have mobile phones, you have smart grids, smart homes, smart buildings, and all sort of systems that could receive software to offer smarter functionalities. So we are dealing with a type of system of systems. Well, considering that these systems have received software, so they started to exhibit a software architecture. And when you consider the large-scale system formed by other systems, so the software architectures comprise the inner systems, the constituent systems, the entire structure and how the systems interoperate between themselves. And this type of systems exhibit dynamic architectures, because when you think about a smart city, you have an autonomous car that join the smart city, and other autonomous cars are leaving the smart city, and airplanes coming and going, and people with their mobile phones coming and going. And so there is an impact on the structure, the instantaneous picture of the city. And so this type of systems are highly dynamic due to the operational independence of the constituent systems. So considering this type of systems, the number of systems involved, when you think about New York City or São Paulo, if each one of the autonomous cars will be a constituent system, so we are dealing with potential millions of constituent systems, and so we need to deal with such complexity. One way to do that is using models, because models are abstractions of the reality, so they are processable by computers and software, and so it's easier and more effective to process this amount of information using software than doing it manually. So we could use models. The problem is because this kind of models must represent and capture not only the static properties of the smart city as the inner constituent systems that form them, but also the dynamic expressed by the interoperability between them, and the changing structure and all kind of dynamics it exhibits. So we need some solutions. We needed some solutions for software engineering of system of systems. So we started in August of 2013, and we initiated the project, and the first step was the conduction of 2 systematic literature reviews, one about model-based engineering approach for system of systems, and another one about software architecture description for system of systems. The results we obtained from these systematic reviews were the externalization of the state of the art, and we concluded that we had a lack of notations to support the specification and prediction of both the static and dynamic dimensions of system of systems. For example, when we consider UML, SysML, or CML, they are static language. They were the only one available at that time, and they are not successful to deal with some concepts that are essential for system of systems. For example, the idea of abstract architectures, because the abstract architectures capture the potential types of systems that can be involved in a system of systems. The problem is because this type of representation is not possible in UML, because when you are using UML or SysML, you only can capture the pre-existing constituent systems or the predicted constituent systems. So you must define exactly all the systems that will be part of the smart city, for example, and this is not possible, that it's not feasible. The idea of multiple constituents, because when you use UML or SysML, you use a sort of models to describe multiple perspectives of a same and unique one system. When you have multiple systems interoperating, so you would need to interoperate or exchange or communicate many models, each one of those set of models representing one system, and so this is costly, this is potentially unfeasible, and this is really complex and error prone as well. It's not possible to represent dynamic architectures as well using UML or SysML, and it's not possible to do a prediction about the effects of a reconfiguration on the source behaviors, on the functionalities that are being provided by the system of systems. So between 2014 and 2015, we selected a set of formalisms we could use and started the design of a solution. Simulation emerged as an option for source dynamics. The problem is because, simulation models, even being an option to represent the dynamics of systems, lacked some precision about the distinction between the types of systems. For example, in a simulation model, all the systems are only systems. You can't distinguish between a smart building or a smart home or an autonomous cars. Every type of systems is only one system, and so we couldn't distinguish, so this hampered the precision of the representation. They also do not support abstract software architectures. Environment modeling is not native to the simulation formalism, and when you are dealing with system of systems, we deal with low level of abstraction because we are dealing with systems level abstraction, and the behaviors are specified using state machines and ports, and this is really error prone. It's low level of abstraction, it's complex, it's close to the Turing machine formalism, and so on. This is not like feasible or good to be applied. So in 2016, SOS-ADL emerged as an option to represent SOS. SOS-ADL was created with an inherent operational semantics. It means that we already had the definition of an animation for each one of constructs of the language. It means that when you define an operation semantics, you have a recipe to make the models executable. The problem is because this was developed SOS-ADL models and create and that. So this was the first solution we provided. We had SOS-ADL models specified here. We submitted it as an input to the extend model transformation, the transformer called MS for me, and it ran the source simulation. The problem is because the environment was not actually represented, and the simulation execution used to demand feeding, because when we were using the simulation to represent the dynamics of the system of systems, we used to do it to to feed or stimulate the simulation manually. And when you think about some couple dozens of systems, so this is totally unfeasible to do manually. So we provided a solution to automate the feeding of the stimuli that represent the environment to the simulation of that source architecture. Then we established stimuli source. We included some transformation rules here to automatically generate an artificial entity here called the stimuli generator. These entities were deployed together with the source simulation. So at the simulation execution time, this was feeding continuously feeding the source simulation in a way that we didn't need to do it manually anymore. The problem is because after we solved these in 2017, we also perceived that the simulation models generated using our model transformation had some conflicting instructions because we didn't identify how to group them in a way that they could not be conflicting and not crashing the simulation. So we identified some patterns about how to group input and output event instructions, and so we included some patterns, some rules that materialize patterns for source simulations, and so we generated source simulations with no conflicting rules. After that, we complemented the generation of the simulations with a new structure called the Dynamic Reconfiguration Manager or Controller, because until that we were not dealing with this concern. And so we complemented the solution with some more additional transformation rules here in a way that we were generating a dynamic reconfiguration controller was capable of changing the source simulation, the source structure at runtime, so we could observe the effect of that on the impact on the behaviors being accomplished and delivered by the source. On top of all these advances, we established ASA's evaluation method. It was an architectural evaluation method to evaluate the impact of the dynamic architecture on the behaviors being provided. After that, we perceived that the dynamic reconfiguration used to lead to a mismatch between the first version of the architecture and the actual or current version of the architecture, because due to the inherent changes that used to happen or take place, the versions of the architecture at simulation time were being different from the initial one. So we identified the concept of the architectural drift in system of systems and established a method called backsource. So we established backsource as a reverse transformation approach, so we could resynchronize the actual version of the source architecture with the initial model, so we could realign the models. We conduct many case studies on flood monitoring system of systems and space source. We simulated the Brazilian space systems as well. And we also advanced the idea of systems of information systems, when you have some constituents being information systems. So some lessons we learned was about the coexistence of missions in systems of systems. The idea when you have multiple missions being accomplished or achieved or offered like a functionality by a system of systems. And mediators were the pivotal elements in this kind of in this kind of situation, because the mediators were the elements that were responsible for triggering the mission and swapping the context in the constituents being providing functionalities, providing processing time to the missions. And we identified the need for establishing strategies for scheduling resources and dealing with competition and resources sharing, because the same set of constituents were responsible to deal with multiple missions. We also understood or visualized or realized two different types of missions. One type was the data forwarding missions. This was the mission that took place in the flood monitoring system of systems, because the sensors only sensed the volume and forward them. They didn't know the destiny of that data. On the other hand, when we think about system of information systems like the space system, this was a business process with well-defined activities and a specific order, and this was respect, so we realized two different types of missions. We also perceived that the mapping between software architecture and simulation models led to some semantic sacrifices, because as we didn't have the same level of expression, capability of expression in both formalisms, so it was necessary some adaptations. Some open issues and challenges remained from our work. For example, how to determine the empirical value of simulations, how to be sure that the simulation is really correspondent to the model that is being simulated, and how to base your results on the simulation. The coverage of simulation models is the idea of using simulation as a testing platform, because when you are using a simulation, you have a set of stimuli, you have a set of constituent systems, and you have a set of changes that take place. But how to be sure that you are being exhaustive when using these simulations? How to be sure or to draw strategies to transform the simulation models and platform as a testing platform. Another issue is how to be analytic with simulations, how we could evaluate quality attributes of systems using simulation, how to be sure that interoperability it's being covered in all its parts, how to be sure that availability is being tested, how to be sure that security is being tested. So all these concerns must be covered and strategies must be drawn to that. Another point we had, it was about the scalability of simulation platforms. We tested around 300 constituents in our simulations, and we took 30 hours in a really powerful processor. So if you think you plan to simulate a smart city as New York will be with some millions of constituents, this is unfeasible with the technology we have nowadays. So maybe it's necessary to use some parallel processing strategies. And we only started the concept of architectural drift in system of systems, so we need to explain and expand results and consolidate results about the architectural degradation for souls. So this was my presentation. Thank you very much for your attention, and if you have any further doubts, you can email me here, and that's it. Thank you.